Okay, right. So let me just check a few things, and this would be great if that actually works here in these audio settings. Okay. Welcome, everybody. Today, I'm going to talk about automatic speech recognition and how we can use it for linguistic studies. This is a demonstration of IBM Watson, and as you can see, it is really powerful. All right, here we go. Okay, let's just wait until the program's done. It still takes a little bit. There we go. So now it's done the recording. So what you could see is that it worked pretty well. And this is very interesting because it just had basically my laptop microphone input, which is not very good. So you in the Zoom room, you've got my microphone right here, but my microphone on the laptop is not very good. And also this was set to US English and it worked nonetheless. Right. So that's basically what I'm going to talk about today. How can we use this basically for linguistic studies? And first things first, you can basically find all resources of these presentations on my private website. So you can find the slides there, a test file that I'm going to work with, and also the scripts that I prepared for that. So also, I don't know whether I actually make it in time, because I actually squeeze a lot in here. I talk about ASR in the first part, and then LabCAT basically in the second part. Right. So first of all, what is automatic speech recognition? Well, very principally, it's the process and the related technology for converting speech signal into the corresponding linguistic entities. So for example, words usually, and this is implemented in a device, a computer or computer clusters very often these days. So in a nutshell, it's basically about
pushing
this
transcription work to the next level.
Audio doesn't work. Just check that, or I just have to change this up.
Pushing transcription work to the next level.
Okay, into this, right? And this has been a research field for roughly 70 years. So this is not necessarily new technology. We've seen this in the past, but the usual applications were usually something like a simple response. Do you want an appointment? Say yes. Yes, something like this. But recent years, we've seen great advancements due to, first of all, the exponential growth of data that we have, especially speech data, and also, of course, a drastic increase of computing power. So Moore's law still applies. If you compare the average smartphone 10 years ago to the one that we've got right now in our pockets, there's been a great difference. And very importantly, the successful implementation of neural networks in the last decades. Right, so today's applications are, of course, much more versatile and much more powerful. We've got voice search, automatic captioning, which you can find in YouTube, also personal digital assistant systems. So if you think about Siri, Alexa, stuff like that. But what I'm, of course, very interested in is transcription work. So if we basically ask the question, how does ASR work? I just have to say that I haven't got enough time for kind of discussing this. So just a quick overview. If you want to learn more about this, you can basically see a great presentation by Microsoft Research. There's a lecture on that, which provides nice insights. But the basic architecture of an ISR system, or of most ASR systems, are composed of these parts. So in the first step, we've got signal processing and feature extraction. So we've got different means of acoustic filtering. And then the first important kind of aspect there is the acoustic model. So in probabilistic speech modeling, an acoustic model always tries to find the most likely sequence of phonemes. And this can be done by hidden Markov modeling. That was the usual approach, but today we also have got, of course, neural networks involved. And then also including to that, we've got the language models, which is always trying to find the most likely word combinations. So if we just visualize this very simply
in a weak condition,
if we've got such an audio input, right, let's maybe listen to that again.
In a weak condition,
the acoustic model could provide a phoneme stream like this. And this could, for example, represent this as the most likely kind of transcription in a weak condition. This would be the second most likely, and this could be the third most likely transcription of that. The language model would then go about and then identify, for example, by n-gram searches to see, okay, what would be the most likely word combination? And here we would have actually this one here. So as a result, the third one here is then our recognition result. So both acoustic model and the language model always work together. And we could see this also quite nicely in the live transcription from IBM Watson. So if you've got an audio like this,
pushing transcription work to the next level,
you can kind of see that it starts, for example, with push, then pushing, then for some reason, Washington, but then corrects itself again to pushing transcript, pushing transcription, so pushing transcription work to the next level. So it's always kind of working on the processed audio and always tries to find the most likely equivalent, right? So that would be a rough overview, but I don't really have time for discussing that in detail. And there are probably also other people who could do this a lot better than me. So what I would like to, where I would like to continue, this is just a rough overview of the commercial services that we can use. So these are usually designed, for example, for call centers, but for most of these services, you can also use them via an API. So there's a limited quota in which also you can use this freely. I think for these services as well, but there are of course also others. But there are of course also non-commercial kind of projects. So one very influential one, of course, also for forced alignment was the HTK toolkit. Then we've got the CMU Swings toolkit, and Caldi is a very big project, which is I think also open source, but there are of course lots of other platforms, libraries and projects involved there. What I would like to show you right now is my personal favorite at the moment, and that is IBM Watson speech to text, right? And this is a state-of-the-art ASR system. It makes long sound file transcription possible. And very importantly, it includes timestamps, which provide a rough word alignment. So it does not only give you the words or the most likely words, but it also provides rough estimations of where it starts and where it ends. And it is relatively robust. There are different language models that we can use for that. So at the moment, we've got Australian English, British English, American English. It's relatively user-friendly and adaptable as well. And it is, of course, well documented. So, and it's also free of charge as soon as you've got a light license for that. So you can use up to 500 minutes per month for transcription for free. And above that, they charge you for something like 0.01 cent or something. But it is also accessible for academic users via the web mouse interface. And that is exactly what I would actually like to show you right now. So as a first step, I would just like to briefly illustrate how this works if we harness that via an IPA. Let me just see. And I basically, prepared a random kind of sound file for that you can also find on the website.
As well as gratitude. And for the first time, what feels like forever. I also feel a sense of hope.
So
there is light.
A short extract from a speech by Nicola Sturgeon, Scottish English. So we don't have a language model for that. But if we basically apply a script where we use the IPA and extract the information and then convert it into a text grid, we can kind of directly see some results. Just need to rearrange a few things here. If I can do that, okay. Here you go. Right, so you can also find the script right here. Sorry, this is a little bit difficult to set up. Okay. Okay, it's already working. So let's just fingers crossed that my internet connection is stable and that the server is not bumpy. Okay, right, here we go. Let me just see another thing. What's this text grid? Internet connection should work. Okay, takes a little bit of time. So I think the audio file is roughly a little bit less than a minute. And there we go. So that worked. There we go. So basically what we've got right here are now two kind of text scripts with an utterance transcription and a word transcription. So let's just have a quick look how that turned out. Right, here we go. Okay.
As well as gratitude.
Okay, let's just go on.
And for the first time in what feels like forever. And for the first time in what feels like forever.
Sorry. Okay, so that looks good.
I also
so that
feel
would
a sense
be
of
kind of the overall approach here. So we can kind of use ASR for that via an API. However, as I said, there is also a way in which we can use the BAS Web Services interface. And you can basically, go to, there we go, the BAS interface, so to say, and there's also a form for ASR. So you can just go to that and just basically log in with your institutional account. Also, if you are not from a European institution, and this also works for British universities, so I checked that with my Glasgow account. So if you're not from a European university, you can also apply for a BAS user license. You just have to say that you're an academic user, basically. Okay, so what we basically have to do, just go to step 2, is upload that here. And again, fingers crossed that my internet is going to hold this. Then we set the language up to English. So we can go for Great Britain and then choose IBM Watson. I hope you can kind of see this. Yeah. And then as an output format, we've got different options, but we can take prod, for example, and diarization. I just clicked false at this moment. And then we basically produce the same step. So that is a way in which we don't have to use a programming language, but this will, if the server connection is stable, will also produce a similar result. Just wait a little bit. So these are the steps for that. Looks well. There we go. Okay, so that worked. So now we've also got a text script transcription. Let me just cut that out, put that here. And if we open this up, we can also see that it's pretty much done the same thing, and we don't need a programming language for that. Step 2, test file. Now, what we have right here via the webmaster interface is that we only have got word alignment, right? So we only have got words, but this can easily be converted also into an utterance transcription, which then in the end makes it a lot easier for correcting the stuff. So if you can go this word by word.
Well, gratitude.
Right, but we can also transform this into an utterance transcription, and I've also written a script for that because, that has helped a lot. So that's also something that you can find on the web page, right? So that's already done. If we open this up, let me just get to prod. Got loads of stuff on here. There we go. Utterance output, we basically have got the same result. So here again, we've got this now transferred to an utterance transcription. And if we go through this, this makes correction a lot easier. Right. Okay. I think I'm running out of time. There we go. So that would be an option for easier correction. So that is basically just a demonstration. You can, of course, find all the stuff online as well. And I basically just switch over quickly to LabCAT. So what is LabCAT? That is a browser-based linguistic research tool developed at the New Zealand Institute of Language, Brain and Behavior. It's basically a storage for audios and videos, and it enables automatic but also manual annotation on different layers. It includes the search function with regular expressions, which is very nice, and it is also very compatible with other linguistic software. So LabCAT basically takes in different text formats. So for example, prod, text grids, ELAN transcripts, but also transcriber transcripts, and also of course CSV TXT files. It also is compatible with other annotation software. So if you've got the MU web app, and prod can be handled via LabCAT, you can have forced alignment through that. Also recently, we've got libraries for R, Python, Java, and Node.js. And also we've got other compatible software and compatible dictionaries. So this is basically the structure, what I would do, but I don't know whether I've got enough time. So that's basically what LabCAT looks like. So this is a kind of a visual interface, so we don't have to have any code in here, but we can simply just upload a transcript. So working. Okay. There we go. And I'm just going to choose a file that I prepared for that. So that is basically the same file that I had. I just changed the name. Right. Go to monologue, upload. All right. And then it's basically uploaded to the system. So if we have a look at the transcript, we can now see that this has been divided into the different utterances.
As well as gratitude. And for the first time in what...
Which we can also change. So we've got a visual interface. And also due to the fact that I connected Celix to that, we can also, for example, find parts of speech tagging, which is automatically inserted, right? So you can basically see that in another layer, and this can be exported as well. We can have morphological parsing information, which also comes from Celix, right? So what fields like forever, we can have a syllable count. It's also in the Celix database, and that connects directly to that. And as well as, wait for it, speech rate. Due to the fact that we've got a syllable count, we can then also automatically calculate speech rate. Okay, and just as another one, if you do the math and if you set up a few files in here, you've got a very powerful search function. So let's just go for search everyone. And then you can basically decide what exactly you want to search in your corpus. So I've seen a presentation on the hue in Scottish English by Ulrike Gut, which is also on our database. So what we can do, for example, if we look for orthography, let's just basically look for that. Then, for example, exclude the O, and then wait, use a little bit of regular expressions to search that. And then this basically splits out all the matches that we have. So here we've got all kind of matches in our database. We've got 337 right now. And the good thing is also that when you open this up, so when you just click on that, this is then also highlighted in the transcript itself and points you to that direction. So we can listen to that.
We will make the case today for using the powers of this Parliament to invest in public services. We all...
Right, so you basically can open this up in Praat as well. There we go. So this is kind of connected to Praat. So you can edit this as well. You can also edit this right here with the transcript function. So this basically makes an efficient kind of analysis and data preparation much more easier. Right, okay, and now I just have to switch over to the discussion. Right, so for ASR, the advantages are, of course, that you've got kind of an automatic pre-processing of data, which can be a great assistance. It can be time-saving, depends, of course, on the performance, but if you do the maths, that was like 47 seconds of speech, and it took like 7 seconds, 10 seconds or something for the trips to execute. It's a less kind of tedious workflow, and sometimes there are, of course, also less random errors. So that basically means if you've got several transcribers, this is kind of more systematic because it all runs through one system in the beginning. Limitations are, of course, it depends on the research project, but manual checking and correcting remains necessary. For IBM Watson, it's not so much an issue, but if you've got sensitive data, of course, data protection is something to think about. There's a limited amount of language models, so it doesn't work for all varieties that well, and the performance basically depends on the input. So basically, the higher the audio quality, the better usually. So if you've got really bad audio quality, it will not perform as good. The more structured the speech, the better. So if you've got radio broadcast political speeches, it's better than just really speeches with loads of false starts. The less regional the speech, the better, so to say. So basically the language model has to adapt, and also the speakers involved is a little bit of a question. For ASR, it's of course very user-friendly, it's well documented, and there's great support by the authors. It's compatible with different file formats, of course, and we've got this nice search function. Limits are that some add-ons, for example, HDK, are really difficult to set up, or at least that's the case on Windows. So that took me at least a week or something, but that might also just be a Windows thing. Right, so these are my references. And these are basically also useful resources, but you can also find that. So thank you very much for your attention.